So here we are at the end of Unit 4, and we're going to talk about solar radiation and the Earth and how that affects climate. I am throwing watersheds in here just because I don't really know where else to put it. But we're going to be looking at solar radiation and the seasons, global wind patterns, geography and climate, and finally the weather phenomena that are El Nino and La Nina. So here are your learning objectives for watersheds. Again, make sure that you look over these. So basically a watershed is just an area of land that all drains into one spot. So anything that occurs in a watershed is going to affect what the water body that it collects in. So if there's impervious surface like blacktop or driveways, roads, parking lots, things like that, that's going to cause runoff and decrease infiltration into the ground. If there's any kind of industry or farming, that is also going to cause water pollution, and that is going to end up in the collection area. You can see in this picture, I have a bunch of tributaries, the little rivers that feed the bigger river, and then the bigger river ultimately will go out into a larger water body like Long Island Sound or into an ocean or into a lake of some sort. So whatever happens in a watershed is going to affect the collection of water. Watersheds are really determined by topography. So, water flows downhill. And so at some point there's a breaking line where the water will flow in a different way, and that's part of a different watershed. So now moving on into the basis of this PowerPoint, we have solar radiation in the Earth seasons. Again, make sure that you look over these essential knowledge points to make sure that you are knowing what you need to know. So here we are with solar intensity, and basically the latitude of where you are on Earth, or the latitude of Earth, is going to affect the amount of solar intensity on the Earth's surface. So if you look at this picture below, at the equator or around, so depending on what time of year it is, but usually around equinox if we're looking at it that way. So the solar radiation is really hitting at a really direct angle, and it's super, super concentrated in one area. Whereas if you look at that spot in the north on that picture, you have solar radiation is actually spread out more, and so it's not as intense. And so that is the reason why, right, it's warmer in summer and cooler in winter, because as you're pointed away from the Earth, the concentration is a lot larger, and when you're pointed towards the Earth, that concentration is a lot more concentrated. That didn't really make sense, but you get what I'm saying. Anyway, okay, so if you look at the picture on the left, right, you have the northern hemisphere is in summer, the southern hemisphere is in winter, and you have that direct sunlight is above the equator, and so that's why we get more direct sun or more concentration of sun during the summer. And in the winter, when we're pointed away, that really direct vertical ray is actually is south of the equator, and so we have a much more spread out concentration of solar radiation. And so that's the reason for the seasons, is that we are, right, pointing towards the sun in the summer and away from the sun in the winter. And here is a fun little video. If you download the PowerPoint, you'll be able to play it. I'm not going to play a video within a video, but please go ahead and watch that. And they're starting. Okay. So moving on, we're going to look at global wind patterns. And so before we even talk about that, we need to talk about how heat is transferred on Earth. So you have solar radiation. Basically, you have these waves of energy that are coming from the sun, and that actually ends up hitting the Earth, and that warms the Earth. And so Conduction is a transfer through direct contact of solid substances. So, for example, like heating a pan, right? That pan is directly on the element or the fire and gets really, really hot. And so that's conduction through direct heat. Get it? Conduction, direct heat. Okay, but convection is really what we're looking at. And so this is the primary way that energy is transferred on Earth, and it's the movement of heat through air, or actually liquid also, because we looked at it through magma. We're also going to look at it through the oceans, but convection is really based off of the fact that warm rises. And so if you look at this picture, right, you have hot air is rising, which makes way for air to come in and fill that void. And then as it rises, it's cooling and then ultimately falls again. And so you have this convection cell, or right, this circular motion of air. And on Earth, there are actually 6 convection cells. And if you always start at the equator, then you will hopefully not get this wrong, is that the equator is really, really hot. And so the air, right, it heats the land, and then the land heats the air, or the oceans also, right? And that will heat the air, and the air gets really, really warm, and it's very moist because it has a lot of water, because it's in equatorial regions in the ocean, and that warm air will rise. And when it rises, that air, right, condenses, and ultimately moisture gets released from that. So you have condensation, which then falls out. So at the equator, you end up with this very warm, right, you have the warm air rising and it falling out. So you have a lot of precipitation. So it's wet at the equator, which is why most of the tropical rainforests that we see are at this latitude. And then when the warm air is rising, right, the cool air sinks. And so these are really based off of 0, 30, 60, and 90 degrees. And so you can see on the previous, or maybe 2 slides earlier, it was like Tropic of Capricorn and Tropic of Cancer. They're really around the 30 mark. So, keep that in mind. All right, so to start, like I said, if you always start at the equator, you're almost always going to get this right, is that it's very, very hot. The sunlight is most intense, and that surface air will then rise and expand. And as it expands, that rainfall drops out, and you end up with a lot of rainfall. So in the tropics, right at the equator, you end up with warm, moist climates. The air is then cooling, and as it cools, it descends and ends up coming back around to the equator and doing the whole thing over and over again. So as that cooling air descends, you end up with pretty low humidity because that moisture is dropped out of the air. So it's very, very arid. There are lots of deserts around 30 degrees. Next up, once you go from the equator, from 30 to 60 degrees, you have what we call a Ferrel cell. And so the Ferrel cell, that right, the moist air is rising at 60 degrees, and then again creating that precipitation, and then the cool air is descending at 30 degrees. And finally, at polar cells, you have 60 degrees to the poles, so 90 degrees, and that warm moist air in the 60s is rising just like it did in the Ferrel cells, but right, it diverges. So one's going south, well, in this picture south, depends what hemisphere you're in, but you get the picture, right? And then as the air is going towards the poles, it's cooling off and then dropping. So you end up with very little precipitation again at 90 degrees in those polar regions. And so that's why we consider the tundra almost like a desert, because there's very little precipitation there. And so, like I said before, you end up with these different climates at these latitudes. So at 0 degrees, you have very, very wet climates, and at 30 degrees, you have more dry climates. You can see in the picture that I put here, these are the world's deserts, and so most of them are at about 30 degrees. That Tropic of Cancer, Tropic of Capricorn, again, right? It's not exactly 30, but you get the point, right? So those deserts are really occurring in those latitudes. The ones that are, you know, kind of outliers, there's different reasons for those, and we're going to talk about them in a little bit. So very dry climates in the 30 degrees. Then you have wet regions near 60 degrees, if you think about it, like, you know, those temperate rainforests. And then, again, dry at the poles. But it's not as easy as that, right? We have these convection cells, and that's all well and good, but the Earth is spinning around the axis, and so it's deflecting these air currents to the west or east, depending on where you are, in the north or south. And so in the northern hemisphere, these surface winds, so the winds that are running along the surface of the Earth, are getting deflected right in the northern hemisphere and towards the left in the southern hemisphere. And so these cause the prevailing winds, and they distribute heat and moisture more so than just going in a straight line. So here are the prevailing winds. We have gone over these in class, or will have gone over these in class whenever you're watching this PowerPoint. But so hopefully you have some understanding of how this really works. It's kind of tough for me to explain it in a PowerPoint and not in person. I'll do my best right now, right? But let's start at the equator and work our way north. So if you are going, right, if your wind is running from north to south, so from 30 degrees to 0 degrees, you see those surface winds are running from north to south, and then that wind gets deflected to the right. And if you are going from 30 to 60, right, those winds are going south to north in that convection cell along that surface current there, and those are getting deflected to the right. And then in the polar regions, you have winds running from 90 to 60, so south to north, and again are getting deflected to the right. Now I know if you're looking at it, you're like, what? It looks like it's deflecting to the left, but you have to keep in mind the direction of the wind. So if you're like picturing the wind blowing, right, from south to north, it's going to get deflected to the right according to how the wind is blowing. So if you don't understand this, like I said, it's hard for me to explain it in a PowerPoint, but please, please, please make sure that you come to me and go over this if you don't get it beyond what we've done in class, because this is actually a little complicated, and hopefully we can help you out. And so these prevailing winds are actually named for where the wind is coming from, and that's how winds are always named. The trade winds, which are from 0 to 30 degrees, those are called the northeast trade winds and the southeast trade winds. And the westerlies are in that band from 30 to 60 because they're coming from the west, and the polar easterlies are coming from the east. Moving on to geography and climate. So like I said before, not all climate is based off of these winds and, you know, and the precipitation and temperature that they cause. There are other reasons for different climates. Have you ever been on the beach and felt the cool breeze in your hair? Well, that's because water has a very high heat capacity. It means that heat is absorbed and released a lot more slowly in water than it is on land. And so the land will get very hot during the day and warm the air above it, and that warm air will rise, and the air from the sea will actually move in to replace it. So you get that sea breeze coming in towards the land. So we call it a sea breeze because it's coming from the sea. On the other side, you know, in the nighttime, the water is actually warmer than the land, and so, relative, and that warm sea is warming the air above it, and so that warm air rises, and the air from the land moves in to replace it, and so you have what we call a land breeze. Another, um, you know, piece of climate that I want to talk about is called the rain shadow effect. And so you can see in the picture at the bottom here that as the air moves in from the ocean, it's carrying a lot of moisture. And so if there's mountain range in the way, that that mountain will actually block the airflow, and the rain will fall out on the windward side, or the side that is, to the wind side of the mountain. And on the other side of the mountain, the leeward side, it's very, very dry air. And so if we go back to that map of where our deserts are, you can see that, like, in the western United States, you end up with more wet climates towards the Pacific, and drier climates on the other side of the Rockies. And so this is the reason why. Another climate that I want to talk about is an anthropogenic climate, and this is something called the heat island effect. The heat island effect is basically, you have a city, it has tons of impervious surface, very, very black usually, and so therefore it has low albedo. It absorbs a lot of heat and therefore warms the air above the city more than it would if it were like over a forest or something. And so so we call it the heat island effect because it's an island of heat. And it also is exacerbated by the fact that the buildings are blocking the wind flow, and so if there's less wind, then the heat will kind of stay stagnant more. Not to mention there's a lot of traffic in the cities, and so all those motor vehicles are also releasing heat as well. And here we have different air masses, and we're not going to get too much into weather. We really want to focus more on global climate, but this is really the reason for our weathers. And so what is happening is that in a low pressure system, you have very cloudy and rainy weather, stormy weather. A lot of hurricanes are very low pressure systems. And so what happens is low pressure and density of the air causes the air to actually rise and cool, and so that condenses into clouds, and when there's too much water, it falls out, aka precipitation. And so in a high pressure system, you have very cool, dense air, and that dense air will fall down to earth and end up being pretty fair weather because the air mass has already let its precipitation out somewhere else. We're going to talk about major ocean currents because oceans are really influence climate quite a bit. It's redistributing heat in the oceans, and the land masses that are nearby are actually going to be affected by what's happening in the oceans. So like I said before, water has a very high heat capacity, and so those oceans are absorbing a lot of heat from the sun's rays, and they hold onto it, and it takes a while to let it go. So again, we're going to start at the equator, right? Those equatorial regions have super warm water because of that direct sunlight, right? That concentrated area of the sun's rays. And so what happens when water warms up is water actually expands, and thereby actually raising the surface of the water at the equator. And then once it's up, it runs down by gravity away from the equator, and those prevailing winds are pushing the water either one way or the other, depending on where you are on the globe. And this causes gyres. So the gyres are those circular regions. Remember that our planet is a sphere, and so this map right here is not. It's a two-dimensional depiction of what our Earth looks like. So you can see here in between North America and Africa, you have this one gyre in the Atlantic, and then again in the southern hemisphere. And you can notice that in the northern hemisphere, those gyres are moving clockwise, and in the southern hemisphere, they're moving counterclockwise. And in the Pacific, you have the same as well, right? So there are 5 major gyres in the world. When you hear about the Great Pacific Garbage Patch, that is that northern hemisphere Pacific gyre that's there where the trash really gets caught up in. But really, there are trash islands in the middle of every single gyre on Earth. So there you go. So in the deep ocean, you have this really, really cool nutrient deep water. And so when warm water moves away, it leaves room for this cooler water to come up. And this is called upwelling. And it's actually super important for fish stocks because it is supporting primary productivity. Lots of nutrients, gives us lots of phytoplankton, which is our primary productivity in the ocean, and that supports large populations of fish and really the rest of the food web in the oceans. Another reason for water to be moving is through something called thermohaline circulation. So thermo meaning temperature, haline meaning salt. And so because water is freezing in the Arctic, it leaves the salt behind. And so the concentration of salt in the Arctic is actually higher than the rest of the Earth. And so that cold, salty water is very, very dense up in the Arctic, and it sinks down to have these deep water currents. You have these cold, deep water currents moving along, and then as it gets to the equator, it warms up and rises in the ocean. So there you are again with convection, this time in water, but convection nonetheless. And so take a look at the map on the right there, right? You have let's start at number 2, actually, right? It's very, very cold. Water's freezing. You have this cold, salty water, and it's dropping down in the ocean, and then it comes up, and as it's moving around the Earth, getting to the equator at number 4 there, right? It gets warmer, and then ultimately, has a more surface current, and it's much warmer. The number 1 right there is a very important current that you guys should probably know. And it is called, oh my God, I know it, and I'm spacing. Oh man, I'm sorry. It's called the Gulf Stream. Oh, sorry. Right, so number 1, you have the Gulf Stream. That's one of the ones that really affects us. So that current right there. And so just to kind of like tie it into climate change, if you think about this thermohaline circulation, this is like the conveyor belt of the ocean. It's so, so important for distributing heat around the globe. And so when you have glacial melt, right, when you have that land ice that's actually adding fresh water into the system, not only is it warmer, but it's also less salty. And so this can really disrupt this circulation around the globe. So we're looking at major climate changes around the globe because of these melting glaciers. So finally, we're going to talk about El Nino and La Nina. These are phenomena that happen in the Pacific Ocean. So we're going to look a little bit closer at these. I think what's important to know is that these are not anthropogenic. They're actually natural phenomena, and these change ocean temperatures as well. So let's take a look. This is a hilarious little bit by Chris Farley from Saturday Night Live about El Nino. I like to show it in class for a little giggle, but that doesn't work in my slideshow. So either download the PowerPoint to get a little laugh yourself, or perhaps I'll play it for you in class if you're lucky. So El Nino is actually, right, the boy, right, the little boy or something. But really, it has nothing to do with children. So let's take a look at what happens in a normal year and then what happens in an El Nino year. I'll show you some maps. And here we go. So in a normal year, you have these trade winds that are blowing this warm coastal water from South America over to the East Pacific. So over to Australia, over to the South Pacific. And so when that warm water moves away, what's happening is that you have upwelling. Like I said before, that's that deep ocean water that's very, very nutrient rich and can support that phytoplankton. And so it's super important for the food webs of the ocean right there. And then in an El Nino year, what's happening is that those trade winds, so the winds that are from 0 to 30 degrees, are actually either slowing down, stopping, or changing directions completely. And what that results in is that warm coastal water along the Americas are actually staying there. They're not leaving room for the upwelling. And so the upwelling does not happen. Deep nutrient waters do not come up to the surface, and then you have a decline in fish populations. Not only that, because that surface temperature is so warm in the ocean, it's actually altering a lot of Earth's climate. So you have a lot warmer, wet weather along the tropical Western Pacific and cooler and dry weather along the Eastern Pacific. So you actually have a natural climate change. And so here's a picture as promised, right? So let's look up at the normal year. Again, you have these trade winds that are blowing westward, right there in the northern hemisphere would be the northeast trade winds. And so they're blowing west, and that warm surface water is getting pushed away from South America over by Peru and ends up causing, wet weather along the South Pacific there. So in Australia and Indonesia, you end up with a lot of warm, wet weather on that side of the ocean, where on the Peru side there, you end up with a lot drier, cooler weather. And in an El Nino year, what's happening is that the trade winds are either dropping or stopping. So or even reversing. And so those warm surface waters are actually staying along the coast of South America there. And that water is not going over to Indonesia. And you end up with a lot of precipitation in the Western Pacific. So along South America, and in Australia, Indonesia, you end up with a lot drier weather. So who cares, right? This is in Peru. We're not in Peru. But actually, what's happening here affects the entire globe, really, in their local weather. So if you look around the world, you have, in an El Nino year, you have very wet weather, like I said, along Peru, that South America edge there, because remember, we're looking like more in equatorial regions. But this also affects us here in the United States. So a lot of times we'll have a really dry winter, so not a lot of precipitation in an El Nino year, but also, right, you have very dry, warm up in the Indonesia area, wet and warm up in Japan. So in El Nino, you can really get a lot of different occurrences when an El Nino is actually happening. And it's kind of arbitrary as to why they happen. And here at the bottom is a hyperlink where you can see NOAA. So the National Oceanographic Atmospheric Association has a blog about El Nino, and some years are worse than others. This year wasn't so bad, but in other years it was really strong. And so depending on how that goes, it'll affect the weather around the world. And here in the United States, like I said, it will affect us, right? Because of the jet streams and all that stuff. What ends up happening is you have a very wet winter in Southern California and a very dry winter in where we are and up into right, I don't know, I wouldn't call that the Midwest. What would you call Ohio? I don't know, but you get my drift. So La Nina is actually completely opposite of El Nino. If you think, oh, I know what El Nino is. Well, if you don't know what El Nino is at this point, definitely come talk to me. Um, but it's opposite. So basically, the trade winds are actually increasing. And so what's happening is that those waters get pushed really, really hard into the Eastern Pacific, so into Indonesia and Australia. And you have very, very cold water along the coast of Peru. And so the coastal waters are cool, a lot colder than normal, and you have a lot of upwelling. So you have a lot of primary productivity. Not to mention the weather all around the world is just going to be a little more extreme than what it really would be. So for example, if we have a La Nina year in Southern California, you probably would go into drought because it's so little precipitation, as opposed to in an El Nino year, you have a lot of precipitation. And thus concludes our PowerPoint on climate. Oh, sorry. And here's a little video if you feel like you want to download the PowerPoint and watch an explanation of an El Nino.